Okay, so we're going to take a step away from the book for a little bit and talk about proving a causal relationship, that is, proving a cause and effect relationship between two variables. So there's a few things that I want you to get out of this presentation, so let me list them to you. Things to know from this presentation would include 5 different things that you would look at in trying to establish a cause and effect relationship, that is, something causes something else to happen. I want you to know what a longitudinal study is. So that's a particular type of statistical / epidemiological study, also known as a cohort study. Understand what confounding variables are. That's certainly a big part of this discussion. Now, for our discussion today, we're going to talk about global warming. This is going to be kind of our example in showing a cause and effect relationship. So part of that means you're going to have to understand the difference between climate and weather. Now, you don't necessarily have to have one opinion or another about global warming to get an A in this class. I'm simply using this as a demonstration. So don't worry, I'm not going to look at your opinions in one way or another and decide what you should get in this course. It's going to be completely different. So one thing that you want to look at and examine is that if you have a cause and effect relationship, that you have the correct temporal sequence. The cause, then the effect, chicken, then the egg, or vice versa. But it should generally have the correct temporal relationship. Replication of studies. If there is a true cause and effect relationship, then study after study should be showing that. It shouldn't just be, well, this one study says this, and then other studies say something different. An example of that would be a connection between cell phone use and increased chance of brain cancer. Studies haven't been very conclusive. There have been a lot of studies all over the map. It's not been conclusively shown one way or another at this point. A dose response. We'll talk about what that is. So dose response. And here's our longitudinal studies. They're going to help us rule out confounding variables. And the picture here is somewhat humorous. One of the things you'll look at, one of the things you like to see are double-blind studies. If you're testing a medicine, then the researcher doesn't know and the patient doesn't know what they're getting. That way, any results they see aren't attributed to a bias by the part of the researcher or the part of the participant. And last but not least, you should be able to explain what's going on. You know, why something's happening. How does the cause produce the effect? So you should be able to explain what's going on there. Now we'll go over all of these again in detail, along with the answer to that one question. You know, what does the weather do? Or what's the difference between weather and climate? So we'll start out there. What is the difference between climate and weather? Does anyone know? Are they the same thing? No.
Isn't one like more atmospheric and like one is kind of more closer to the Earth? Is it just like
No. So you'd be talking about what's happening in like the stratosphere versus what's happening the troposphere. That'd be different. Yeah.
Weather's more day to day. Climate's like over years.
Exactly. So weather is what's happening outside our window right now. Climate is long-term averages, trends, etc. The way I like to express it is that weather changes by the day, climate changes by the latitude. That is, how far you are north or south, etc. Those are going to be your climate changes. If you travel farther south, then it's going to be a little bit warmer. So climate is long-term trends and variation. So, all right. So we'll start out with that understanding, and then we can talk about how you can establish a cause and effect relationship between two variables. And I'll use, like I said, as a case study, global warming. Now, the the most challenging part for that discussion is right here, the correct temporal relationship. Usually you like to see the cause and then the effect. And you can see that quite clearly with cigarette smoking. With cigarette smoking, the graph in blue represents the rate of cigarette smoking in the U.S., and then the graph in red represents the rate of lung cancer deaths. So you can see that one graph kind of mirrors the other one, but it's been shifted a little bit, right? And that shift is really the lag that it takes for lung cancer to develop. It takes 20 or 25 years for somebody to develop lung cancer based on lots and lots of cigarette smoking. So you can see that lag pretty good. So it's pretty easy to see the cause and then the effect. In fact, we're seeing that again in a different way this year. For Christmas, there's a shortage of Christmas trees. Well, that's kind of odd. Why would there be a shortage now? Well, it takes 8 or 9 years to grow a Christmas tree. So put yourself back 8 or 9 years ago. What was happening in the economy 8 or 9 years ago? The Great Recession, right? You know, stock market went down, home values went down. Maybe you guys probably weren't really paying attention to that stuff 8 or 9 years ago. It might not have been on my radar. But 8 or 9 years ago, there's this big recession. So, you know, are a lot of tree farmers, people who grow Christmas trees, are they going to be anxious to grow Christmas trees right then? I mean, they might be losing business. They might not be able to afford it. So that slowdown then is being seen now. So there's a lag. So one lags behind the other. You can see the cause and then the effect. We're seeing the effect now. It's a little bit nuanced when it comes to global warming. Global warming, and in this graph, it's not so bad, but some graphs, it's tough to tell, does the temperature go up first or does the carbon dioxide go up first? Which one's going up first? So in this case, you've got temperature in blue and temperature also in red. It's just different ways to get at the temperature. And in yellow, you'll see estimates of global carbon dioxide. Now, you also see around those estimates a little kind of wing. What do you suppose those wings are that surround each dot here? Margin of error, and what do we call that back in chapter 7? Confidence intervals, yeah. So what happens is that they can look at ice cores to help establish ancient carbon dioxide levels and also ancient temperature levels. Hey, good. How you doing? Excellent, excellent. Thank you, thank you. All right, all right. Hey, appreciate that. So we'll catch up to you. All right. You know him? All right. So that was actually a little bit more than an impromptu visit from my department chairman. It's a little test because I want to see what kind of a consensus we can build. I'm going to pass around two different sheets. I want you to write down the color of his suit and the color of his shirt. So he was just there seconds ago. Let's see what kind of agreement we can come into. All right? So, hang on. So, that was a little bit of a setup there. But we'll see. Let's just see. All right, so we'll come back to that part in just a little bit. I'm very curious to see what kind of consensus you guys can come to. All right, so the temporal relationship, it's pretty nuanced. You know, sometimes the temperature can go up, and then the carbon dioxide levels will also increase. Sometimes it happens in the opposite direction. Part of that is because the hemispheres warm differently, and another part of it is, you know, just the nature of carbon dioxide. And you can kind of think of it in terms of a bottle of pop. What happens when you first open that bottle of pop? Yeah, it's going to fizz. It's going to release its carbon dioxide, right? Now, the amount of carbon dioxide you get is going to be related to how warm it is. So if it's warmer, you're going to get more bubbles. If it's colder, you're going to get less bubbles. And the same thing's going to happen with the Earth. I mean, sometimes, if levels of carbon dioxide can go up and then it creates a temperature increase. Sometimes it happens in the opposite direction. Part of that, again, is wrapped up in something called thermohaline circulation. It's basically the ocean currents. They're the big driving force of climate on the Earth. There's massive ocean currents that help keep England warm when they should have colder winters like we do. But they're a little bit warmer because they get warm water from up near the Caribbean. All right, so this is not exactly the nice relationship that we see with smoking, but it doesn't necessarily mean that a rise in CO2 doesn't cause an associated rise in temperature. We're going to look at other graphs extending back further in history that'll show that. Now, what about replication of studies? Oh, question? Yes.
So, is the basic just a temporal relationship? It's just asking for causation or causation?
The temporal relationship, generally you like to see the cause and then the effect. The smoking, then the lung cancer. Or the exposure to asbestos, then the lung cancer. Or what else? People who don't exercise and eat a healthy diet, getting coronary heart disease, that kind of thing. Usually like to see the cause, then the effect. In this case, there's kind of a feedback loop, and they're both kind of intertwined. So it's not quite as clear that there's one then the other. And in fact, like I said, it's nuanced. If you go to this website here, theskepticalscience.com, if you go to that exact website, you'll see a very complete discussion of this. And even for myself, I had to read it a couple times. It's there, but it's just challenging. All right, thanks for the question. Anything else? Replication of studies. If there is a true cause and effect relationship, study after study after study should show that. Now, maybe not all of them will show it, but the preponderance of studies should show that. You remember, every time we do a statistical test, there's that alpha % chance you could reject the null hypothesis when you shouldn't. That can happen. So studies can be in error. And there's also a type 2 error that you can look at too. So, is there a consensus? Does everybody agree that there's global warming? Well, not really. I went to this website, and found out that there's 31,000 Americans with university degrees, including over 9,000 with PhDs, that signed a statement that basically they don't think that global warming is a man-made phenomenon. So, well, it's a pretty sizable number of people that don't agree. Of course, it doesn't necessarily mean that they have degrees in climatology. They just said they have university degrees, which also implies that a lot of these are bachelor's degrees. Which, okay, there's nothing wrong with a bachelor's degree. Hopefully you guys get some. But let's take a look at a little bit more credible paper. By the way, this one's from the Oregon Institute of Medicine, which I've never heard of them. And I looked them up, trying to find out, well, where is this place? And what kind of courses do they teach? Well, they don't teach any courses. They don't have a football team. It's just someplace in this little know-nothing town in Oregon. So, okay, whatever. So a more credible study came out a year ago, and they concluded that basically that there is no consensus amongst scientists that global warming is real. Now let me explain something about the way they did this. They looked at the abstract of a lot of journal articles. And the abstract's kind of like the executive summary at the start of the article. And if it did not explicitly state that the cause of global warming was man-made, then they put that in the no position category. So basically they said, well, that's a zero. It's not a plus, it's not a minus, it's a zero. And that really seriously biased their conclusions, which is why they they said that, well, there's really not a consensus amongst scientists here. If you apply that same level of determining whether or not somebody believes or not believes in global warming to other well-established theories like plate tectonics. Does anyone know what plate tectonics is? There's the plates on the Earth that move around that cause earthquakes and volcanoes and mountain change, etc. They've shaped the Earth, and a lot of its climate, in fact, throughout our history. That theory has been pretty well established since the 1970s. But if you take Toll's method of deciding whether or not there's agreement or disagreement and apply it to plate tectonics, then there's no agreement that plate tectonics is real either. So I'm not sure that his methodology is correct. This one's interesting. The percentage of people who believe that smoking causes lung cancer has actually gone down from 92% to 91%. So I thought that was pretty well established. So we'll see. Now, my question to you is, before I show you what I thought was the gold standard of studies on whether or not people agree that there is global warming, what percentage would you find convincing? If you were to ask, 100 scientists, do you think that global warming is a man-made problem or not? What level of agreement would you find convincing? Would you want 50 of them? 75 of them? What level? 85? 85? All right. What else? What other numbers? 95? All right. Logan?
I was going to say 95 too.
95? All right. 95. Cool. Anything else? Would you be good with 90? Okay. 90. So the last paper that I found, I thought was pretty well done, showed that 97.2% of climatologists think that global warming is a man-made problem, and that 97.2% of these studies. So, wow, that's overwhelming. That's even better than the number of people who agree that smoking causes lung cancer. I still can't get over the fact that actually dipped a little bit. I'm like, wow, I guess they're smoking the cheap stuff. All right, now let's see how you guys did. So let me exit this for a second. Let's see what level of agreement you guys had. Navy blue, light blue, dark blue, light blue, brown, light blue, gray, white, gray, blue, black and white. All right. Gray and white, gray and white, gray and white. I think people were maybe copying. It's like, okay, I'll go with him. All right. So let's look back here. Let's see. Slideshow view. Or is it current? It should be current slide, right? Slideshow. There we go. From current slide. All right. So how did you guys do? Well, it's actually a light blue. If you took a look at him, he was wearing a light blue shirt and some gray. So not exactly a consensus here, but better than my morning class. So anyways, kind of fun, I hope. Let's move on to another thing here. Dose response. Dose response means more of the cause gives you more of the effect. So that's what you typically like to see if there is some kind of a cause and effect relationship. So here's a longer look at the historical record of CO2. Like I said, you're getting this from ice cores and other historical sources. So, I mean, you have to do something because CNN and the Weather Channel weren't around back then. So, okay. But take a look at these things. We don't have a nice zoomed in version of the time scale as we did with our previous slide, but it looks to me like they're going up pretty much in lockstep, don't they? Temperature, if one is up a little bit ahead of the other one, that's still fine. We talked about the cause and effect relationship. But boy, certainly looks like more carbon dioxide, higher temperature. Lower carbon dioxide, lower temperature. That looks like the kind of dose response that I would expect from a causal relationship. Yes?
It kind of looks like it's going in a cycle.
It does. It's very, very interesting that you looked at that and noticed that there is some cycles there. And
Sorry, they were saying, I read somewhere a couple years ago, but they're saying that the poles are like reversing something that does that every so
the pole, yeah, it's interesting phenomenon that the
and it's,
magnetic north switches.
yeah, that's what's doing part of the global warming or something. It's
I don't
somewhere.
think it has anything to do with the poles, but I'll talk about what it does deal with.
That was switching, that was doing.
It's called the Milankovitch cycles. Yeah.
Like, I've seen this before. I'm pretty sure I have. Like,
Okay.
don't we also have to be careful with like the graphs since it's not starting at zero? Because I've seen like the full one, and like that line right there is represented. Like, it looks like huge.
Well,
inside the big blown up one.
that's true, but take a look at the temperature. I mean, the temperature range here is, 20 degrees.
I totally agree.
That's yeah.
Like,
No, I agree. In fact, that's one of the things we did in this course is we showed you some graphs that didn't start at zero, and it can, depending on the scale, exaggerate differences. But I think these are this is not it's not a scale designed to try and exaggerate a difference that's not there. I think this is more than just background noise. Well, I mean, you take a look at the tops and the bottoms. I mean, that's a difference of 20 degrees. That's a noteworthy change. I mean, if our temperature was 20 degrees warmer, we'd be like on the equator. I know. Well, but see, now there's a fallacy here. A lot of people might say, "Oh, it's going to get 60 tomorrow. Gee, we're experiencing global warming." But that's really a problem of weather. You can get warm days. That doesn't really say something one way or another about global warming. Now, is it consistent with global warming? Yeah, but it doesn't necessarily prove it. What proves it is going to be the long-term trends. And these long-term trends that you see here, these are over hundreds of thousands of years, do show that more of CO2 marches in lockstep with temperature. So it's a pretty good graph. Now, what it doesn't show, as well as it could, is this bit at the end here. Take a look at this spike starting around the 1850s when we really started to mechanize a lot of things. Wow, that's pretty high. And it doesn't exactly tell all. If you were to step outside today, I did this yesterday, the levels of carbon dioxide in the air are about 407 ppm. So it actually is kind of funny. It has this little rise and fall. It depends on summer in the northern latitudes, the northern hemisphere. In summer, we're out more and doing more things. We're driving around more. We're going to put more CO2 into the atmosphere. And then it dips a little bit in winter, and then it goes up again in summer. So if you look at the long-term pattern very closely, you'd see a kind of a sawtooth pattern, but a general upward trend. And boy, that's really, really up there. That's potentially bad news. All right. I just found this one kind of amusing. People. Oh, but somebody on Twitter. I know you're a climatologist, but somebody on Twitter said this. Go ahead. Question? Well, I mean, you look back here. More CO2 seems to go along with, correlate very nicely with higher temperatures. And lower levels of CO2 seem to correlate and go along with lower temperatures. So you're seeing that dose response. More of the cause gives you more of the effect. So more CO2, higher temperature. Lower CO2, lower temperature. Now, the problem here, is that this is such a huge spike. We have never seen that in our geological history. So we don't know what to exactly expect from this. But I do note that I think 15 out of the last 16 years have been the warmest in recorded history. I mean, every year it's like, oh, it's like a broken record. Oh, another warmest year in recorded history. I mean, we're seeing that now. And the fear is that at some point it's going to accelerate. So, okay, longitudinal studies, also called cohort studies. The nice thing about these is that they can help us rule out a confounding variable. And let me discuss what a confounding variable is. So, a few things that must be present to be a confounder. I think I actually should have 4 here, but okay. Confounding variable is a variable whose presence changes the relationship between the independent and dependent variables. So, okay, what would be an example of a confounding variable? If you were studying the connection between heart disease and obesity, then if you had 2 groups that you were studying, and one of them had a lot more smokers with high cholesterol, who didn't exercise, who had a bad family history than the other one, then those variables could muddy the waters. They could change the relationship between obesity and CHD, because those are other risk factors for coronary heart disease. So you kind of want to make sure that if you do have these kinds of other variables, that they're evenly distributed amongst your experiment and control groups. Confounding variables have to be associated with both the risk factor of interest and the outcome. And to be a confounding variable, it has to be distributed unequally amongst the control group and the experiment group. One last thing, confounder can't be a step along the way from your cause to your effect. It has to be an independent variable. It can't be the tar that's in cigarette smoking, which binds with radioactive radon in the air that gets down into your lungs and creates malignant cancerous cells. So it has to be something independent of the 2 variables. Now there's some challenges. Let me talk about longitudinal or cohort studies. So there's a couple different types of studies that people use when they're looking to try and decide cause and effect. A cross-sectional study is just looking at people at one time. The problem with cross-sectional studies, and we'll see this in Chapter 11, is that they can only tell if there's an association between 2 variables. Longitudinal studies, or the cohort studies that we're looking at, they study a group of people over time. So they'll follow a group of people far into the future. Now, there's some problems with that. The challenges of a cohort study are that they're costly. I mean, you're following people for years, maybe even decades, and keeping track of them and then collecting all the data takes a lot of time, takes a lot of money. And the other problem that you're going to run into is a loss to follow-up. People get bored being in the study, people die, people move, etc. So it's hard to keep track of all of them. There's a lot of challenges in conducting a cohort study, but there's some good benefits. Question? Yes? I'll post the PowerPoint online. That way you can kind of catch things that way too. All right. If you want to take a quick look, is that the one you wanted? All right. So there's some challenges in conducting a cohort study, but there's some benefits as well. So why go through all the expense and the time associated with a longitudinal study? Well, there's a good reason for it. they're flexible. Sometimes as you're doing your study, you need to adapt it. You realize that there's a need for change. So, cool. You can check it. You can change things up as you go through things, or you can measure different variables if you decide that, oh, this might be relevant, etc. An example of the flexibility of a longitudinal study comes from a Pfizer study on sildenafil citrate, which probably no one in this room has heard of. But it was a medicine originally designed for, I think, controlling blood pressure. Blood pressure or maybe cholesterol level. I'm pretty sure it was blood pressure. And after a while, they decided, you know what, it's just not working. So Pfizer contacted all these guys and said, all right, hey, you know what, we're gonna call it quits on this study early, and just give us our test medicine back. And all these old guys are like, no, we're keeping this stuff. And Pfizer got curious. Well, why don't you give us our medicine back? Well, I'll let you kind of fill in the gap. Yeah. So you probably know sildenafil citrate is Viagra. So, all right. But the big thing about longitudinal studies is that what you try and do with your cohort is divide up into an experimental group and a control group. And if you do it in a nice way, then you're trying to balance out the confounding variables. So they're equal. And then any difference that you see in the outcome can be attributed to the one remaining difference, which is are they the case or are they controlled? Do they have the exposure or not the exposure? So that makes it really good for determining a cause and effect relationship, is that you've eliminated all these possible confounding variables. So, is anyone a fan of Benedict Cumberbatch, Sherlock Holmes? Or just going back to Sir Arthur Conan Doyle, says, how often have I said that when you've eliminated the impossible, whatever remains, however improbable, must be the truth. And the point here and the relevance here is that if you have two groups that you're studying in a longitudinal study, one has the exposure and the other one doesn't, and that's the only difference, then any difference you see in their outcome can be attributed to that one difference in their exposure. So that's the nice thing about a longitudinal study, is that it really helps in establishing a cause and effect relationship. So let's take a look at a couple possible sources of confounding variables. Catherine, this is getting to what you were talking about earlier. Changes in the earth and physical things in the earth. You could see changes in the amount of light received from the sun, and changes in the earth orbit could also have an impact on climate. Those are called the Milankovitch cycles. It's named after a Serbian mathematician, Milutin Milankovic. And the interesting and funny thing about him is that he was able to do all these calculations because he was a prisoner of war in World War I. And I don't know how this came about, but he was placed under some kind of house arrest. And once every 2 weeks, he had to go to report to Turkish authorities and say, yep, I'm still here. And then he went back to doing his research, which included calculating for various parts of the globe all kinds of numbers about how much sunlight and the angle and the tilt. He did this for a long, long time. But he was the type of person who enjoyed this kind of menial, repetitious calculation. And we named the Milankovitch cycles after him. Volcanic eruptions can contribute massive amounts of CO2 to the atmosphere. In fact, at one point in Earth's history, they think that this is what saved us because Earth was pretty much frozen over. We think we got rescued by a huge outpouring of CO2 from volcanoes. Climate change naturally in the past, so maybe it's doing it now. So, different sources of possible confounding variables. We're just going to look at two of these. The Milankovitch cycles. There's three different things that change in Earth's orbit. How much of an elliptical path it changes, or how it follows. So it's called the eccentricity. Then you have the precession of equinoxes and the Earth's tilt. All those are going to affect what gets sunlight and how much and where and when. And all of those have an effect on the Earth's climate. In fact, Catherine, you mentioned that earlier. Aren't there some cycles? And this is what those cycles are. It's the Milankovitch cycles. Now that and the amount of sunlight, if global warming was not a man-made phenomenon, then the amount of sunlight that you would receive according to the Milankovitch cycles would actually suggest that there should be a cooling, a mild cooling of the Earth at about this point. But we're not seeing that. We're seeing an ever-increasing, ever warmer world here. But if it was because of sunlight and not man-made gases, then what you would expect is that the upper atmosphere would be warming and the lower atmosphere would be warming. That's what you would expect. In fact, what we see is the upper atmosphere is cooling, but the lower atmosphere is warming. So it kind of eliminates that as a possible confounding error, confounding variable. It's not the Milankovitch cycles. It's not how much sunlight we're getting. It's something else. And I would point the finger at the extra CO2 that we've been emitting for the last century and a half or so. Plausible causal mechanism. In establishing any cause and effect relationship, you should be able to explain why the cause produces the effect. You should be able to draw that line between those two variables. So what's that look like if you're to indict CO2 as a cause for global warming? Well, it's pretty simple. You have solar radiation that comes in from the sun. It warms the Earth. A lot of that heat is radiated outwards. But when it gets to these upper levels in the atmosphere that have a lot of the nitrogen, methane, CO2, and nitrous oxide, that warms those molecules which radiate the heat in all directions. Now with a thin layer of these greenhouse gases, a lot of that escapes into space. But when you continually add more CO2 to the atmosphere, you're making that layer a lot thicker, and a lot more of that heat gets radiated back towards Earth. So you're warming Earth. Basically, it's like putting a thicker and thicker blanket around the Earth, is what you're doing by adding more of these greenhouse gases. Now, CO2 is the one that gets all the attention, but there's other ones as well. Nitrous oxide, which is what your dentist gives you. Methane. What's the big producer of methane?
Cows.
Cows, yeah. And not to put too fine a point on it, but cattle farts. A lot of cattle farts. So, all right. So we understand the mechanism. It's there. It's physics, and no one denies that. It's pretty well understood. All right, so those are the 5 different things that that would help you establish a causal relationship. Is there anything on that before I look at some type 1 and type 2 errors? Just kind of review those with us real quick. Doing all right? Now, I've taken as my null hypothesis that global warming is not man-made. If you wanted to establish that global warming is man-made, you should probably put that in your alternative hypothesis. Why? Why does it matter? Why should I put it here and not in HO? When you do a hypothesis test, which one of these is assumed to be true? Yeah, the null hypothesis. If I want to show that global warming is man-made, I should probably not put that in the null hypothesis, because then I'd start out by saying, well, let's assume global warming is man-made. Let's assume it's true. No, you should prove it's true. So with that, let's take a look at some type 1 and type 2 errors. If global warming is not man-made and the data fail to reject H0, that's a correct decision. If global warming is man-made and we reject H0, again, that's a correct decision. So type 1 error says global warming is not man-made, but we think it is. What are the consequences? If we do something about global warming, then, and it's not real, maybe it's just a natural cycle for some reason, then we're going to increase our energy. We have to find better sources, cleaner sources of energy. Might lose some jobs in the fossil fuel industry. Could be inconvenient. You might have to take more public transportation or share rides. There could be higher prices for commodities. There's a lot of stuff that's made with oil, and all those prices are going to go up. So there's a lot of real consequences for working on global warming, especially if it's not real. What about the other consequences? What if global warming is real, but we don't do anything? We're like, you know what? Data doesn't really suggest that we should do anything about it. Well, there's some consequences there too. Consequences of a type 2 error. Severe weather. Boy, we saw that this year, didn't we? Hurricanes, Houston, Puerto Rico. I imagine Puerto Rico's still recovering. I can't imagine that they're past their hump yet. Warmer winters are great, but there's a price for that. Spread of more illnesses. Remember 2 summers ago, what was the big illness in Florida? One that had everyone all afraid. CDC was really in a panic. Zika, the Zika virus, yeah. So if you have milder winters, you're not killing off the bugs that carry those diseases. They're going to move farther and farther north into the northern latitudes, like Michigan. So, yes.
They were also saying that because you're melting the ice caps and stuff, there's other stuff trapped in there, like the animals or whatever, like dead
Yeah.
bugs or dead animals, and the animals that are alive now are eating those.
Oh,
And that's how we end up with
newer diseases?
well, old diseases. That
Old diseases that are coming back?
Yeah, we haven't seen them in a long time. So
That would.
there's that too.
So we got that to look forward to, which is nice.
Yeah.
All right, yeah. So, exposing these older dead animals could expose us to bigger and better diseases. Woohoo! All right. What else? You could reduce areas for agriculture. I mean, there's only a small percentage of the Earth's available surface that we're prepared to live on, and reducing that area that's available for agriculture in the face of a growing population, that sounds like bad news. Rising sea levels. An overwhelming percentage of the world's population lives along the coast somewhere. And if sea levels rise substantially, it's going to be more flooding, some huge problems there, relocation. It's going to change migratory patterns. We've already seen this happening now. Changes of patterns of hibernation, more extinction of species. I mentioned this earlier. It's going to interrupt the thermohaline circulation. And this is a big deal. It's the biggest driver of our planet's climate, is the circulation of the ocean's currents. In fact, at one point in Earth's history, you had what's called the Miocene salinity crisis. It's when the Straits of Gibraltar closed, and it meant that you couldn't refresh the Mediterranean Sea with salted water. And it changed the salinity content of the oceans, and theory is that it put us into an ice age. The Earth's climate can be very, very sensitive, so who knows what would happen there. And then health threats. Air pollution is going to be worse. So a lot of problems, a lot of consequences of a type 2 error. All right, what's going to happen? Well, tough to project in the future because, we've only got so much data. You can project it out as far as you want, but how far out does it make sense to make these projections? Tough to tell, but I'm not sure I would like to see these trends continue. We'll see what happens. So, in summary, there was 5 different things we discussed, 5 different ways to prove causation. You should know those 5. You should know what a longitudinal study is. And as part of our discussion in longitudinal studies, we looked at what confounding variables were. You should know the difference between climate and weather. So those are the things you should be getting out of our discussion here today. Is there any wrap-up questions here? All right. Thank you. And work on a little regression assignment next.